Thank you, Mr. Gupta, for invitation and the organizers for the opportunity. So today I'll be talking something technical about the LNG CO2 removal and the economical insights that we can get from advanced simulation software. I'd like to acknowledge my co-author for this work, Dr. Anand, from our company. Okay, to brief up the presentation of today. So I'll talk about the modeling techniques that are currently available in the market commercially, and I'll go to what is actually mass transfer rate based. Later we have a case study that is an operation of LNG CO2 treatment, both absorption and regeneration. A physical case study with simulation model, optimizing the economics and also the results. So later I'll explain the use of the software for calculating the propagation of uncertainty in design as well. So let me go to the next slide. So before we begin, I just want to quote one famous quote from Mr. Hore. He is a computational scientist from he's the one who created the sorting algorithm and was given the best award. So he said there are two ways to construct a software. So in the first way is construct a software very simple, such that there are obviously no deficiencies, or make the software so complicated that there are no obvious deficiencies. The first method is create a software very simple, which is fundamentally right and have no deficiencies at all to find. Second way is create a software which user can't understand the back end, and it is so complicated that there are deficiencies which are not obvious. So I promise that I'll give some confidence for you to select the model when I complete my presentation. So let me talk about the modeling techniques for LNG absorber and strippers. Nowadays there are so many models available in the market. So first one is ideal model, that is ideal stage based, as we chemical engineers learn this in school, where we model column using ideal stage based methods such as McCabe-Thiele and apply the efficiency to find number of real trace, calculate the theoretical stages. So this is a legacy model. I am not saying it is the wrong model. It's a legacy model. It's been there for decades. It treats each tray of an LNG absorber as an ideal stage, which is really not. So these are ideal stages, not real trays. And we do is make the theoretical stages and do some theoretical superficial adjustments. So that's what we do with ideal stage modeling. This is one type of modeling LNG absorber stripper loop. So these models are extensive, and we adopt them based on the structural deficiencies. They definitely have structural deficiencies, because no process in real world is ideal. So no process in real world is obviously ideal. They are so sensitive to operating conditions, throughput, and many other parameters. So this is one kind of modeling we have been through. The model I'd like to focus more today is mass transfer rate based model. So it is not so futuristic. It's been there in the market for 30 years now, and it is better to represent the gas absorption system and rigorously model it by tray basis. So as you know, in absorption process, there are so many sub-processes happening. If you take a single layer of an absorption column which is packed or tray, if you consider the molecules, the gas is so turbulent, the hydrogen sulfide or carbon dioxide from the gas should travel from the turbulent gas to the interface, and from interface there is a physical solubility where the gas dissolves in the interface, and the gas travels from the interface to the bulk liquid, which is typically amine. And in the bulk liquid, since it's a chemical reaction absorption system, there is a chemical reaction happening, and after the reaction happens, there is a diffusion of reaction products and heat as well, because it's an exothermic reaction. So there are so many processes that are happening in a single absorber right at the moment. If you have a physical LNG absorber or stripper, So these are all been included in the mass transfer rate-based model, which is structurally correct, and it represents very closeness to the physical phenomena what is actually happening inside a column. So if you ask me, there are so many commercially available softwares, ideal-based softwares, equilibrium-based softwares in the market to simulate my amine model. What is so special with the mass transfer rate-based model? So when you say, when the strong fundamentals, that is, if you see it in the perspective of a building, if the foundation is very strong, the building will stand so longer. The same way applies to software as well. So if the fundamentals, the foundation itself is very strong, such as the fundamentals in mass transfer, heat transfer, and the approaches, the software will be able to predict the plant performance instead of assuming it. So there are so many applications you can do with mass transfer rate-based model. We are the original inventor. You can do acid gas removal, you can do acid gas enrichment, tail gas treatment, soap water stripping, LNG, caustic, carbon capture, and so on. You can also do acid integrity predictions, corrosion predictions for different wet acid gas corrosions. And also, it is very versatile. Like there is something called as CAPE Open compliance, which is computer-aided process engineering open. That is, two softwares can talk together. For example, if you have a process modeling environment, and you can plug ProTreat as process modeling component. So the two can talk and integrate as well. So this is a special feature which makes ProTreat so integrative to the downstream Sulfur Pro unit as well. And if you are an operation guy, if you want to troubleshoot your unit, if you want to optimize the plant performance, you can do that as well. So let me go to the case study we did. It is an LNG CO2 absorber. The target is to remove carbon dioxide below 50 ppm, the feed gas, in the treated gas. So the feed is around 113 mmSCFT. And actually the unit is meeting spec, but the thing it is over treating the gas. So there is very much low CO2 in the treated gas, which is kind of undetectable. So the opportunity came here to optimize the circulation rate, the existing system, and save money. So we did simulation using the MTR model, as I said, ProTreat. So it provided us the flexibility to optimize the circulation rate, the amine circulation rate within the system. And we still met the specification. We were not over treating. We just treated the feed gas to meet 50 ppm in the treated gas. In contrast, we also compared the results with the ideal model. Ideal model said that it underpredicted the circulation rate, which was so obsolete. So that was a misleading opportunity for optimization, whereas mass transfer rate-based model helped us to optimize reliably. So this is a case study we did. Let me just quickly give you the values of composition. This is a simulation model, and if you see, the feed flow is 113 mmSCFT, and it has around 3 mole% of carbon dioxide, mostly methane, obviously. And so this is before optimization. Before optimization, the treated gas is around undetectable CO2, that is 0.033 ppm. And absorber is equipped with packing, IMTP, and also it's 18 meters height. And coming to the regenerator, it's a generic valve trace, which are 22 trays, which are 2 pass trays. And the heat duty is around 13 megawatt. This is a base case where the total flow of the amine is 175 meter cube per hour, which is over treating, which has MDA around 40 weight% and piperazine at 1 weight%. Coming to the results of the case study, ideal model literally underpredicted the circulation at 112 meter cube per hour. It said at 112 meter cube per hour, you can still meet the circulation, but reality was different. MTR model said you can meet the circulation, you can meet the specification at lower circulation, but it is not 112 meter per hour, 112 meter cube per hour. So it said at 131 meter cube per hour, you are still able to meet the spec of 50 ppm in the treated gas. So that gave us a steam saving of 5,280 kg per hour. At the same time, if you convert it to economics, it is around 4.43 lakhs INR per day steam saving. This is literally the money left on the table, which is not completely used at all. So reliable models definitely will predict the performance of the plant, can save you operational economics. Here in this case, it's around 15% relative to the optimized circulation rate. Sorry. So why why mass transfer rate-based models makes also economic sense? Here in this case, you saw that operational circulation optimization gave us economic benefit in a sustained way, still meeting the spec. When one can think of maybe the software is so costly we can't afford, so the software investment can be recovered within few weeks of operational savings. At the same time, there are some design guys in the audience as well. It is also beneficial for design people where they can completely avoid the over-designed columns, over-designed regenerators, and cut the design fat and save so much of money. In the previous, we did so many case studies in our previous papers where some of them were from design. Design says that using mass transfer rate-based model saved so much of money in terms of trays. For example, if you save 3-4 trays, it saved so much of lakhs in INR. So this is the way to make economic sense of a process simulation software. I'd like to emphasize all the application areas of mass transfer modeling: gas treating and LPG treating, so water stripping, as well as caustic treating. You can do deep CO2 removal using formulated or proprietary solvents from vendors, or generic amines such as MDEA, DGA and all. You can do trace sulfur species removal such as COS and CS2 from your gas. And you can also do ammonia hydrogen production and CO2 removal with MDA or hot pot process, which is so famous. The beauty of the mass transfer modeling and kinetic modeling is that you can also model your entire sulfur plant starting from feed to degassing and incineration with the highest precision and accuracy. So there is a term called, when you are talking about rate based in absorption and stripping, the term rate refers to the mass transfer rate. So there is some misleading thing regarding the rate in the same absorption process, because there is a reaction that is happening in the process. That rate does not refer to the kinetic rate. That rate should be the mass transfer rate, because absorbers are primarily mass transfer devices. So if you are supposed to ask if you are asked to enter any parameter which is so fancy, such as efficiency, which we can't really see with our eyes, or HETP, so that is not a true mass transfer rate-based model. So true mass transfer rate-based model which only asks the real hardware information. For example, number of real trays, or number of what is the height of the packing, what is the packing, who is a vendor. So similar physical hardware information is only needed by mass transfer rate-based model, no fancy information at all. So that is the only way you can differentiate, you can get to know whether my model is really truly mass transfer model. As I said, for the design guys in the room, if you are having a design for a green project, if you are designing something new, which is not, which is something related to absorption or the application areas I mentioned, there are so many phases, such as in this pyramid, feasibility scouting, for project spec finalization, EPC phase, and also commissioning. So simulation comes under the bottom of this pyramid. So if you were able to remove the uncertainty at the bottom of the pyramid, you can decrease the uncertainty at the top of the commissioning. For example, if you leave...
Can you please complete?
Yeah, sure.
Because we have got 3 more speakers.
Yeah, sure. If you leave 5% of uncertainty at the bottom, it will become 15%. So I'd like to conclude the presentation of the day by saying your model is only mass transfer rate based if it get all the fundamentals correct, each step-by-step process, and it is also economically sound, not only technical. At the same time, the software license payback period is few weeks of trace and steam savings. So these are some of our customers we work with, Indian Oil, Aramco, EIL, ExxonMobil, Sulzer, so all mentioned over here. So as we end, which simulation model would you like to prefer? Is it with obviously no deficiencies or the one with no obvious deficiencies? It's your choice. Thank you.